course right now called Advanced Thermodynamics to about 100, well, it's 80 people. 80. And I don't need a microphone for that, so I don't know why I have one for you guys.
An older crowd.
But I come from Worcester Polytechnic Institute, third oldest engineering school in the country. I work in the Center for Heat Treating Excellence, and if anybody would like more information on that, you can see Roger Fabian. We have brochures. We are always recruiting members, and that's the end of the sales pitch until Roger gets hold of you. Okay, so this is, we're going to summarize some work that I've done over the, well, we've done over the past 5 or 6 years, but we started more than 25 years ago working on these kind of simulations. And if you think back 25 years ago, the condition of our computers, when I wrote the simulation for a very simple carburizing process with very simple boundary conditions and everything, I could go to my computer and hit start and run, and then I could go outside, I could have a smoke, I could go buy lunch, I could come back, and the computer would still be running. Hopefully I'll show you how fast things run now, and it's not because I got better at programming, it's because the computers now run so fast and have such used memory that allows us to do, the potential to do a lot more things than we currently do with these tools. This work was done by Olga Rowan. If any of you follow this area, when she did this, she was Olga Karabelchikova, a nice Russian girl who now works for Caterpillar in their heat treat R&D group. Mei Yang is recently got her PhD, and she's doing one more year with us as a postdoc, working on nitriding and several other things in the area of computational thermodynamics. Danielle Belcito is a PhD student who's got another year plus to go, and she will be finishing soon. Wants to stay in the New England area. And then May, it's Ying Wei, who's currently finishing her PhD at Air Products, and will be available, and I'm pretty sure she will go to work for Air Products when she's done. Lei Zhang is another PhD student in manufacturing engineering who's working on some of this code and some non-destructive evaluations for verifying it. And then finally, Liang He is running an Air Products center in Shanghai right now. So I just point out all those people and what they're doing because our product is not only the wonderful technical thing, but also the people who are coming out available for the working in this in our industry. So what I want to do is, first of all, I will prove to you that I am a professor because there will be equations and graphs and stuff. But I want, but I hope to show you that how useful these codes are right now. So here's the outline. We'll do the modeling. I know there's some people in here who actually do this. And so we could argue about how we fix some boundary conditions and how we do things if they want. And then we'll talk about some specific models for carburizing and carbonitriding. Tomorrow morning I will do nitriding, which is much different than this because here we're in austenite, and that we're down in the ferrite and carbides region for nitriding. So it's a much different process to try to simulate. There we go. Now, any questions for Dr. Sisson? Okay. Well, if you want to solve these, you have to have the solution to the heat equation, the Fourier's or Fick's second law, and where D is a composition-dependent diffusion coefficient, X is distance, and we just, for different geometries, you just have to put in different constants. And so to make life easier, we'll just talk about doing it in one dimension right now. So you just have to solve this. And if you want to solve, I always ask students, what do you do with a partial differential equation? And the answer is solve it. And then the question is, what do you need to solve it? And you need to know the initial conditions and the boundary conditions and the constants that are in there. So for this equation, you need the initial conditions, boundary conditions, and you need to know the diffusivity. And you can do this for anything that's in the system, and today we'll talk about carbon and nitrogen diffusion. But keep in mind, everything we do works for any izing you think of, aluminizing, chromizing, boronizing. I don't know, there's got to be some more, but this works very well with aluminizing when you want, if you understand the phase diagrams and things. So here's the diagram that explains what we're doing. We have a surface treatment schematic, and you start off, we're out here in the gas with some carbon potential, and in here is you're inside the steel, and we have to get the carbon from the gas into the steel, and it does this across this boundary layer. And we simply model that with a mass transfer coefficient. So we just use some beta that we determine experimentally, and it's fairly straightforward. To do this, we just need a good scale most of the time, because if we know the mass, the weight gain due to carburizing, we can calculate that. We also have several other ways to get at that and compare to the literature values, etc. Fortunately, it's not overly sensitive to that number. So one of the numbers we need to know is beta, and that can go in as a constant, or you could put it in as time-dependent, temperature-dependent, composition-dependent. Pick your dependence if you like into the code, because we solve these equations numerically. So our initial condition is uniform concentration. If you don't want that, then put in another one. Okay. normally we're starting off these processes with 0.1, 0.2, 0.25% carbon in the steel, and then we need to know, like I say, this could also be put in as a function of position. And sometimes you may want to do this for special application. So the boundary conditions is semi-infinite, and so we have there's always some place deep in the metal that's still the initial concentration. And when you learn this in your Introduction to Materials courses, they told you that this was a constant, and they gave you, and the D was a constant, and they gave you the error function solution. And frequently that's close enough for what people want to do. But that surface concentration changes with time because of the mass transfer there. And so in gas carburizing, we set the boundary condition this way. We say, okay, we need to know beta, and so this would be a flux balance. The flux is coming in, and it's equal to the flux that's going out. And what you do is, if we know this and we know the diffusivity, we can calculate the surface concentration when we know Cp and beta. And so that's how we do that. If we're doing vacuum carburizing, we have a whole other situation. In vacuum carburizing, Cp is infinite to get started. And so what you have then is a flux at the surface. So you'd say, okay, I'm going to determine the flux at the surface, and you say, so we have this experimentally determined flux, and we do the same balance and then get the same concentrations there. Again, that flux is can be determined with weight gain on the part. And it's a function of temperature and what the fraction of your gas is, acetylene or cyclohexane or methane or whatever you're putting in. And so that's very furnace specific and gas specific number. So beta determination is, we said we got a weight gain, but we've actually, this is just to show you we set up a situation where we solved this for a constant beta, and then we generated the curve, and then we calculated the area under the curve to give us the flux, and then we went back in and calculated beta, and we can see here's what we started with, and here was our calculated value. And so what we do all the time is set up a problem we know the answer to, generate the solution, and then use that data to go backwards to see if we got what we started with. Students just love to do this. And they're shocked sometimes when it doesn't work out. So diffusivities, we decided to use the diffusion coefficient as a function of carbon concentration. And so what we found from literature and also from a lot of data that Oli generated, that we see an increase pretty much like this for any steel. And depending on the grade of the steel, whether it's a 10 or a 51 or an 86 or a 48 or a 93 or a pyrovis or whatever it is, that they pretty much follow this same curve. And so they're just moving up and down. And so what we do is we say, okay, they all have the same activation energy, and for each steel then we give an A, B, and a D, and so then we can have this. And this just is one of the subroutines in the program to give us as the D at any concentration. And this is a significant enough variation that you need to include it, I think. Not that when you use constant diffusion coefficient here, you don't get real close. Okay, but this is where, and it's semi-difficult to get these numbers experimentally as a function of composition when you don't have a constant surface, but you have beta. And so you're not meeting the boundary conditions for a Matano sort of analysis when you do that, for those of you who worry about such things. But if you read the papers that Oli wrote, she figured it out. Okay, so here we go for carburizing. We set it up this way, and for gas carburizing, we used one boundary condition with a constant beta. For vacuum, we used a constant flux. Both of those are experimentally determined. We said it was infinite, and so this is the kind of result we get going in. People will go to say, geez, how much carbon am I putting in to the surface, and is there any danger of forming carbides? And so if you say, I'm carburizing up here at this temperature, and you look at your iron-carbon phase diagram, here's the solubility limit for that, and then you're in the, the austenite plus cementite region. Well, that's wonderful. It gives you a good guideline, but on the other hand, that's not what the alloy is doing. So here is the isopleth for the 9300 series, and so your 9310 would be over here, right? So here's what you have, and if you're carburizing here, this 9300 has the lowest solubility of most of the kind of alloys we work with, and so if we exceed this, we're in the cementite region. What we find is 9300 series gives us a pain to generate what we want when we do the experiment because we ignore this. So if when we do this, we exceed that, you form a layer of cementite, and that pretty much stops things in their tracks because the mass transfer through cementite on the surface is about 0. And so that brings it to a grinding halt. So you have to always stay below that. And so we're actually working with our partners to figure out how best to do that. And so that's an important thing we're working on. And so one of the things that Ying builds into her version of the code is it keeps track of the surface concentration. And so in this case, here's a plot of surface concentration of carbon during, this is probably during a vacuum carburizing step, but it doesn't make much difference. And once it gets above 1, then we're up here we have austenite and carbides. And so after about 20 minutes, 15 minutes, we actually have exceeded the solubility. So we would expect that at some point we start to make carbides. And so if your first boost diffuse cycle is 1 hour, then you spend a lot of time growing carbides. And so what happens is the concentration of carbon in the austenite stayed here, and you've spent all this time making carbides, and the flux isn't coming through. So the scheme that people do is a whole series of pulses, and you can see how that works. So you pulse and diffuse, boost, pulse and diffuse, pulse and diffuse, pulse and diffuse, and then it works much better. So if you have those, if you ever wonder why there's a lot of short pulses for some of these systems, that's what they're trying to get around when they're doing that. And so Ying, when she wrote her version of this for the work she's doing, the code keeps running, but a little red light comes on and gives her a printout that says you've exceeded the solubility now. Don't be surprised if you're getting funky results at the end. And we find we do. Okay, so this is just another thing you can get from that. This is showing for gas carburizing. We did a lot of experiments, and you always pick the ones that are best. And so you can see here the simulation, and the carbon concentration is measured, and that's close enough for us. And then we put the micro hardness on here, and if you do it just right, you can futz with the scale so they fall right on top of each other. I don't know why we do that, but it does look good. But people say, geez, the micro hardness is 0.2, 0.6 carbon. No, you got to read the other side for the micro hardness, but you see how you can do that. And so for, you know, I show you 1018 and 8620. We always agree well on those. For 8620, once you get up above 0.6 carbon, the hardness flattens out. These are all as quenched. We're working on as effects of tempering to give you other graphs on that. So it works, and it's worked probably 100 times. So moving on to carbonitriding. Carbonitriding, we studied with I'll say a standard sort of process where you carburize for some period of time, and at the end of the cycle you add ammonia. So you put in a little ammonia at the end. And so what we did was 0, 15, and 45 minutes, and 5, 10, and 15% ammonia to see what happened. And we did these experiments at, again, in a big members industrial furnace. And we fixed the carbon potential. And so once we added ammonia, the dilution brought the carbon potential down, and then we increased the enriching gas to bring the CP back up. So we had a constant CP. So in this case now, you just solve two problems simultaneously. So you solve the carbon potential, and you solve then the nitrogen. I mean, you solve the carbon concentration profile, you solve the nitrogen concentration profile. In this case, we used a constant flux for the nitrogen. And again, it's a function of time, and you can see the kind of results that we got. And then when we did the model, and in this model we use for the diffusivities of carbon as a function of carbon and nitrogen, and diffusivities of nitrogen as a function of carbon and nitrogen, and there's a large effect due to the thermodynamics interaction more than any kinetic thing. And you can use Dictra or some code like that to predict that. So we use some literature value that anybody's interested in. I can show you. It was relatively old equations, but it was from somebody who experimentally had done all these determinations. And so just using their data without modifying it, we got good agreement on the carbonitriding. Let me go back one. Because of this high nitrogen, as quenched, you have a lot of retained austenite. Okay, thanks. You have a lot of retained austenite, so the hardness goes down. And so you really need a cryo treatment to get rid of the retained austenite. So if I should have shown you what the hardness does, and it kind of comes up, and then once you get to the nitrogen, it starts to go down due to the retained austenite. But if you cryo treat it and temper it, then you get the hardness as you would expect. So here's what our tools look like. Here's CarbonitrideTool. There's a nice user-friendly interface, and it goes through the different parameters and gives you various scenarios you can play with, and that's what it looks like. I'm going to demo the tool here for you, so that's why I skipped through that. But conclusion is surface treatment can be successfully simulated, and what you need is phase diagrams, diffusivities, and boundary conditions, and I say that like it's easy. That's all you need. And I think every one of these numbers, particularly the diffusivities and some of the generating the alloy-specific phase diagrams, have put out 3 PhDs. So, I mean, it's not simple. But this can be applied to boronizing. We're starting to do a little work on that with some colleagues. And some interest in doing aluminizing, but chromizing. Anything you can get where you have a fairly high potentials in a gas. And so here's a few references. So let me. Kind of the way around this is is you start off, and here we're looking at materials, and so there's a pull-down menu. And that gives you the ones we have in this version of it right now. We have created these databases for other alloys, and usually they're for specific member companies, so we don't necessarily share those. But so you pick your favorite steel, and actually then the density, actually I'll hit default, and you'll see The density, just these numbers you initially see just where to look it up in a table. So we're telling the computer, then it comes out. You need beta for a mass transfer coefficient, and that's easily modified by typing. You need to know the diffusivity, and that number just tells it where to go calculate it. And then the base carbon. And so then the next step is to pick the geometry. And so we picked fairly simple geometries where you either have semi-infinite or something that's cylindrical and round. So you just have to add an R to the math. And we solve all these using finite difference equations, but it certainly works. We've done it with various finite element methods if you want to go to 2 dimensions. So again, I'll hit that. And then the next thing is the process, and over here for the process, you pick gas or vacuum. I'll pick gas to begin with. Then you got to go back to the process, and again, this is set up for a 2-stage boost and diffuse. We have various versions that have up to 10 stages where you can put in, and for each stage then you put in the temperature and the carbon potential and how long that stage is, and then the diffuse, normally that would get dropped. But we have lots of people we work with where that temperature doesn't drop, but the potential drops, and then the temperature drops in the 3rd step. And so we've got versions of this that handle all that. And then over here, we just hit calculate. That's how long it takes to run. If you blinked, you missed it. Let me show you what happens here. Here's one. What if somebody said, I'm going to drop this down to 0.4. I think that's really cool. I mean, you sit there and you watch the thing move. So if any of you would like to say, geez, I wonder what happens if I make the mass transfer coefficient lower, what do you think is going to happen? Everything goes down. If you actually make the diffusivity lower, concentration goes up, but the depth profile, the case decreases, but the surface concentrations increase when you do this. So if we go say, hey, let's look at vacuum. Now you go through the same step where you put in your materials and you got to put in the default, and then you can change it if you feel like it. Right? And so the question there would be, they'd want to know what the flux is, and then you do again we have a semi-infinite, and then we go to the process. And now we have a series of boost and pulses, boost and diffuse, and what that is for each step, what is the carbon flux? So what's the flux? And then when you're diffusing, the carbon flux is 0, and when you're boosting, it's some value. And we know from Hoffman and some other people that it's not constant, but it's such a short pulse. If you take the average, it works. So, but you could put that in, and we understand that nobody does the cycle like this, but we had to pick something to get started. And so you can modify this so you vary. If you have 10, 20, 30 cycles and the time between them is getting smaller and smaller, then you have to write a script, and it'll go follow that script and then do this.